Section 5.1. What? Section 5.1? Well, I already covered the second, third, and fourth sections. Today we're going to go back and talk about antiderivatives and indefinite integration, and we are going to be starting to look at the shortcut for finding an integral. Number one, let's read what we have first of all. So far we have used integrals to represent accumulation of change and area under a curve. Today we're going to explore integrals as functions themselves. By matching up functions with their antiderivatives, we'll learn some key features of their graphs and equations. So two polynomial functions are shown. Which one is the original function and which one is the derivative? And what features of the graph show this relationships? So I'd like you to pause the video and write down whatever you can to determine which one is the derivative and which one is the function and why. Did you recognize that the parabola would be the derivative and the cubic function is the original function? But why? How do you know that? Hopefully one thing you recognize is that as f, my original function, is increasing, my derivative is positive. It's above the x-axis. And vice versa. When my original function is here decreasing, my derivative function is underneath the x-axis, so it's negative. And also, when my original function has a max or a min, you'll notice that when it has a max, my derivative function is equal to 0. It has an x-intercept. And when it has a min, my derivative has an x-intercept, or it's equal to 0. Now, unfortunately, this next part, number 2, we're not going to be able to do in class. But there is a second page to these notes. And instead of finding the derivative, we're going to be looking for the antiderivative. So I want you to look at these graphs on this second page, and I want you to match up each numbered graph in the first column with one of the lettered graphs in the second column. The first column is going to represent the original function, and the second column is the antiderivative. So I want you to go ahead and pause the video. If you need to, you can pause it on this page so you can see all the graphs. Otherwise, if you've printed it out, and then I'd like you to record your answers here on the first page for number 2. So go ahead and pause the video and see if you can match up those graphs. And I hope these are the pairings you got. So 1, 2, and 3 goes with A, C, and D, and that A, C, and D, if you notice, or your 1, 2, and 3 are all the exact same graph. So what features of the original, the first column, let you know that the antiderivative is in the second column? How were you able to match those up? Hopefully one thing that you recognized was that the first column is the slopes of the second column. And so again, if we look at 1, 2, and 3, these are all -1/2. And if we look at all the graphs of A, C, and D, though they're different, they all do have a slope of -1/2. The second thing you might have noticed is that the power goes up by 1 to get to the antiderivative. And this is probably more visible with number 4 and 5. You should recognize number 4 and 5 as being quadratics. They're parabolas. And hopefully you recognize B and E as being cubics. So 4 and 5 have a highest exponent of 2. B and E are all cubics, so an exponent of 3. The next thing I'd like you to do is, again, pause the video and let me take a minute and see if you can write the equations for 1, 2, 3, 4, and 5, and then also the A, B, C, D, and E that go along with them. So go ahead and write the equations for the first column, and then also write the equations for the second column. Hopefully that first column was pretty easy to fill in because 1, 2, and 3 all were the exact same graph, and so were 4 and 5. Now go ahead and write the equation for the second column that matches up with those, please. These top 3 being linear, I'm thinking that you should have all gotten those. These bottom 2 might have been a little bit more tough. Now, what do you notice about this first column and the second column? Well, especially with these first 3, and we've said it before, this first column is the slopes of the second column. So this is basically f prime, big F prime, of x. And the second column, f of x, is basically the integral of f of x dx. So given a function f of x, little f of x, The most general antiderivative of that is given by the integral of f of x dx equals f of x, big F of x, plus c. And if you remember from the first page, that plus c is because when you're finding an antiderivative, you're finding what's called the whole family of integrals. And so depending on what that c value is, tells you exactly where it is. So if you look at those last three problems, those last graphs that we did, right, this plus c was at 3. This c was -4. This c was -1. So these are all in the same family of graphs. They're all parallel to each other. The same with these two graphs. If we were to put them on the same graph, they would follow the same curve, the same general form. So in thinking about an integral, or to be able to check if you took the integral correctly, one way that you can check the integral that you took is to take the derivative of it. And when you take the derivative of your integral, you should end up with that same function. So if I'm taking the integral of a constant, that's going to be kx. And if you think about if I take the derivative of kx, I'm going to get k. The second one, which I put a nice green box around, is probably the one you're going to use most frequently. So the integral of x to the n is going to be x to the n plus 1 divided by n plus 1 plus c. We're going to do a whole bunch of these so you can understand how this relates directly to that derivative. Also, again, this would be if x had an exponent of -1. If we were to add 1 to that -1, we would get x to the 0 over 0. And that's why we can't have n be -1. So remember, when we were finding the derivative of the natural log of x, that was 1 over x. So the integral of 1 over x is going to be the natural log of x. This needs to be in absolute value bars, because if you recall, you can't take the natural log of a negative number. So those absolute value bars assure us that we're not taking the natural log of a negative number. And just like the derivative of e to the x was e to the x, therefore the integral of e to the x is going to be e to the x. And finally, the sine and the cosine. Remember that the derivative of the sine is the cosine, and the derivative of the cosine is the negative sine. So the derivative of the negative sine is going to be the derivative of the negative cosine is going to be the negative sine. So that's how we get those. Now again, I would challenge you to pause the video and see if you can do at least those first couple of antiderivatives. This first example is basically using this first rule up here. It's a constant, so we're going to get 7x. I just also wanted to show you how this second rule came into play. Because remember, when you have a constant, you basically have an x to the 0. So if I have my 7 out in front, I'm adding 1 to my exponent, and then I'm dividing by my exponent plus 1. And so x to the first over 1, and that's how I'm going to end up with that 7x. The second one, again, we can do the same thing. So I have my 3, and then I'm going to add 1 to my exponent, so that's going to be 3, and then I'm going to divide by that 3, minus 4x. Now we can simplify this, so we're just going to get x cubed minus 4x. Don't forget that plus c. I forgot the plus c on the first one. Don't forget that plus c. I would, and I'm almost sure that Varsity also will take points off if you don't have that plus c. And the third one, well, the constant is just a constant, and we have this rule. I don't know if we've talked about this yet. I believe we have. I can bring that constant out in front. So now the integral of e to the x is just e to the x. We do not have a chain rule in integration. So we would have to first simplify this. We would have to write this, divide that in. We would get x plus 5x to the negative 2 dx. Now go ahead and find the integral of that, please. Again, the exponent is 1, so if I add 1, I'm going to get x squared, and then I'm going to divide by that 2, plus the 5, and again, if I add 1 to my negative 2, I'm going to get negative 1, divided by that negative 1, plus c. So now when I simplify this, I'm going to get x squared over 2. You could also write 1/2 x squared. I'm going to just bring that minus out in front, so minus 5x to the negative 1 plus c, which I suppose we should properly write this as x squared over 2 minus 5 over x plus c. This third one, we will hopefully get into an example like this when we get into u substitution. But for now, I want to remind you to don't forget that you have that handy-dandy card. Looking at the handy-dandy card, the integral of the cosecant squared is the negative cotangent of x plus c. So how do you ever find what that c is if you never really know? Well, in these last two problems, you would need to be given what's called an initial condition, or a point on the actual curve. So find a function f whose derivative is given by that function. So f is going to be the integral of 4x cubed minus 2x squared plus 7x plus 1 dx. So go ahead and find the integral of that. Please pause the video. With a little practice and a little time, hopefully you got that was what the f of x is. But now we're given an initial condition. So my f of x is 8, and I'm going to plug in 3 for all my x's. And I can go ahead and solve that equation for c. When I pop all that into the calculator and I do all this work, I find that negative 89.5 is my c. So therefore I can write my function as f of x equals x to the 4th minus 2/3 x cubed plus 7/2 x squared plus x minus 89.5. Again, I would like you to pause the video and see if you can solve number 3. All I did in the first step was write it in integral form. And now I'm going to go ahead and take the integral. Adding 1 to the exponent is 2. So this is going to be squared. But then I would divide by that 2. So 6 divided by 2 is going to give me a 3x squared. Minus, again, adding 1 to my exponent, I'm going to have an x to the 4th. And then I have to divide by 4, so 8 divided by 4 is 2. And then don't forget your plus c. This is what my function f of x is. But again, I'm told that f of 2 is 3. So 3 equals, and then I'm just going to plug in 2 for all of these. And I can go ahead and solve that. I get 3 equals negative 20 plus c. So c equals 23. And then I can go back to where I wrote my function, 3x squared minus 2x to the 4th plus 23. And you have now learned the basics of the shortcut of integration. If you have any questions, please make sure you come to class and we can go over a whole bunch of these problems.